गुड मॉर्निंग एवरीवन। लास्ट लेक्चर में हम लोगों ने सेकेंड ऑर्डर सिस्टम का रिस्पांस चेक किया था फॉर यूनिट स्टेप इनपुट। सो इन दैट केस there are some summaries like when zeta is less than 1, our response is under damped and the graph is like this, where the slope or time constant t is equal to 1 by zeta omega n, and settling time is again 4t, and at this time the error between actual and desired response is 0.02 or 2%, means response has reached 98% of the desired response, right? And in that case our CT is 1 minus e raised to minus zeta omega n t divided by under root 1 minus zeta square sine omega n under root 1 minus zeta square t plus phi, where phi is tan inverse under root 1 minus zeta square divided by zeta, right? In case second, when zeta is equal to 0, when zeta is equal to 0, the response is undamped and response is like this. In that case our CT is 1 minus cos omega n t. In third case, when zeta is equal to 1, response is critically damped and the graph is like this. When t is equal to 4t, the response reaches 98% and the error is 2%, right? And last case we discussed as zeta greater, and in this case our CT is equal to 1 minus e raised to minus omega n t 1 plus omega n t. And last case we discussed is when zeta greater than 1, zeta greater than 1. In this case our CT becomes 1 minus e raised to minus zeta minus under root zeta square minus 1 omega n t divided by 2 under root zeta square minus 1 zeta minus under root zeta square minus 1, and the time constant t is equal to 1 over zeta minus under root zeta square minus 1 omega n, and the response is over time. The graph of overtimed response is like Ct here T, and this is like this. This is our overtimed response, right? Again, at t is equal to 4t, response reaches 98%, and the error between the desired and actual response is 2%, right? Now, the term zeta omega n, zeta omega n, this is actual damping. Actual damping. When zeta greater than 1. Zeta omega n is actual damping when zeta less than 1. When zeta less than 1. And omega n is called actual damping when zeta is equal to 1, which is critically damped case, right? Therefore, omega n is also called as critical damping. And therefore, zeta omega n divided by omega n, which is equal to actual damping divided by critical damping, is equal to zeta, which is damping ratio. So, अगर हमें डैम्पिंग रेशियो फाइंड आउट करना है तो हम जीटा ओमेगा एन मीन्स एक्चुअल डैम्पिंग डिवाइड बाय क्रिटिकल डैम्पिंग करके अपना डैम्पिंग रेशियो फाइंड आउट कर सकते हैं. Now, characteristic equation for general second order system. Characteristic equation. जनरल सेकेंड ऑर्डर सिस्टम का ट्रांसफर फंक्शन क्या होता है? सी एस ओवर आर एस इज इक्वल टू ओमेगा एन स्क्वायर डिवाइडेड बाय एस स्क्वायर प्लस 2 जीटा ओमेगा एन एस प्लस ओमेगा एन स्क्वायर. And the characteristic equation is when I put denominator equal to 0, means characteristic equation is s square plus 2 zeta omega ns plus omega n square is equal to 0. And on solving for roots, using Sridharacharya formula, I get S1 is equal to minus zeta omega n plus j omega n under root 1 minus zeta square, and S2 is equal to minus zeta omega n minus j omega n under root 1 minus zeta square. So I have two roots for the second order system or second order characteristic equation, and the real part of the roots is actual damping zeta omega n. Real part of the roots is actual damping zeta omega n. Therefore, the real part of the roots represent damping. And this part, we know that this part is equal to omega d. And what is omega d? Damping frequency or damped frequency, right? So imaginary part is, and imaginary part represents damped frequency. Damped frequency of oscillation, right? So real part is damping, and this part is frequency, damped frequency, frequency used for oscillation, right? So this is damped frequency of oscillation, and this one is damping, right? Actual damping. Role of characteristic equations in system response. The role of characteristic equation in system response. So what is the role of characteristic equation in system response? So we see that we have two roots for second order system, where S1 is equal to minus zeta omega n plus j omega n under root 1 minus zeta square, and S2 is equal to minus zeta omega n minus j omega n under root 1 minus zeta square. And let us consider this one is alpha and this one is beta, so this can be written as minus alpha plus j beta, or I can write it as omega d only, and here minus alpha minus j omega d, right? So to understand the role of roots in system response, let us draw a graph like this. The direction is here, and like this one is j omega, and here I have sigma, and uh, this angle is theta. This angle is theta, right? In this case, this region, first quadrant, this region is for when outside the this curve zeta is in between, means 0 and -1. Zeta is in between 0 and -1. Here outside this curve zeta is greater than 0 and less than 1. नीचे में इस साइड जीटा अगेन -1 0. Similarly here zeta is in between 0 to 1. At this point zeta is equal to -1. Here zeta tends to -infinity. Here again zeta tends to infinity. This point is for zeta is equal to 1, and omega d, this is omega d, and inside this circle here zeta is equal to infinity at center. Here zeta is equal to -infinity at this line. Zeta is greater than 1, and here zeta less than -1, and this is for omega n, right? And one thing more, this value is zeta omega n. Here I have zeta 0, here I have zeta 0, right? So zeta, I consider zeta is equal to cos theta, where theta is the angle between the radial line of the roots and the negative axis. And theta is the angle between radial line to the roots and the negative axis, right? This is theta. And what is zeta? Zeta is cos phi or cos theta. So the left half of S plane, corresponds to positive damping. This one is for positive damping. That is when zeta is positive, means 0 to 1. Zeta is positive, that is 0 to 1. and right half is for negative damping, that is zeta less than 0 and greater than minus 1. When zeta is positive, e raised to minus zeta omega n is finite and the system is stable. And when zeta is negative, e raised to minus zeta omega n t is infinite and the system is unstable. The imaginary axis corresponds to zero damping, this line. This corresponds to zero damping, that is zeta 0. Therefore, this is for sustained oscillation. Sustained oscillation or marginal stability. Right? So, classification of the system with respect to zeta can be given as first case, when zeta is greater than 0 and less than 1, I have two roots S1, S2, which are minus zeta omega n plus minus j omega d, and the case is under damped response. Under damped response. Case 2, when zeta is equal to 1, means again we have two roots S1, S2, and that are minus omega n when zeta 1. This case is for critically damped response. Case 3, when zeta greater than 1, now S1, S2 is equal to minus zeta omega n plus minus omega n under root zeta square minus 1, and this case is for over damped response. Case 4, when zeta is equal to 0 means S1, S2 is equal to plus minus j omega n, right? And this case is for undamped response. In case 5, when zeta less than 0, that is S1, S2 are minus alpha plus minus j omega d, where minus zeta omega n is greater than 0, and this is for negative damping. This case is for negative damping, right? Means graphically we can say it as, let this is j omega and this is sigma, and if I have two roots here only, two poles here only, left half plane, then zeta is greater than 1 and zeta greater than 1. So zeta greater than 1 is for over damped case. In that case, response yt will be like this. right? Next, j omega sigma. If I have complex roots here, means zeta is equal to 1. In that case, critically damped case, but it's not like this. This will be like this. Critically damped case. Minus omega n s1 s2 minus omega n here and here. Just a minute. Okay, I was mistaken. This is not like this. Roots are here only. Means s is s1 s2 are only minus omega n on real line, double pole here, right? In this case, I have critical damping, right? And then third case, when I have complex poles, in this case zeta is in between 0 and 1, and the response is under damped response. Response is under damped response. Next, here j omega, here sigma, here I have 0. If I have complex imaginary poles, then zeta is equal to 0, and in that case undamped response, then the case is like this. When I have complex roots, right side of the S plane, means zeta is less than 0 and greater than -1. In this case, our response is like this, right? And last case is if I have two real poles in the right half. In this case, zeta is less than -1. And these both conditions is for the system to be unstable. The response is like this, and these both conditions are for zeta negative. Okay, negative damping, right? Some parameters for second order system, and some responses, right? We'll do it in next class. Thank you.